Evensen, who's the CTO of Embedded for Xilinx.
Thank you. So good morning. So today I'm going to talk about heterogeneous embedded systems. So let's dive into it. So I'm coming from Xilinx. We're doing these SoCs that are fairly massively heterogeneous. So this is the next generation we're going to come out with. And as you can see, there's lots of stuff. It's a little bit hard to read here, but there are multiple CPU clusters there. There's A72s, a few of those. Typically, people run Linux on that, let's say. We have R5s, or what we call the RPUs, real-time process units. Typically, people run maybe something that needs to be safety certified. Maybe it's real-time. They need to have faster response time for external stimuli and so on. We have on the left side, we have AI engines. So machine learning is coming all over the place, right? So basically, DSP engines that can do multiply, accelerate, accumulate really, really fast, but also being able to place and route the different data streams, both through the math engines, the AI DSPs, and to the FPGA fabric that I'm going to talk about. Right? So it's not only the compute, but it's also how do you route the traffic through all these things? How do you have different levels of hierarchies and so on? So, and then in the middle there, we have the more traditional FPGA, or fabric, or programmable logic, as we also call it, which is basically hardware that you can reconfigure out in the field. You can reprogram the hardware, basically, right? So you have a device like this. From a software point of view, there are lots of issues coming up. It's not just one homogeneous system where you can run applications in the same way all over the place. So I'm going to talk a little bit about the issues that are coming out with this, and also some of the solutions that we're working on to fix those problems. All right, first, a couple of words on FPGAs. So I think last year I had a similar slide here, but just really a quick recap what an FPGA is. So an FPGA is one of those things that's different to whoever you ask, because it can be used in so many different ways, depending on how you program it. Right? So in the FPGA, you have something called the programmable logic, the lookup tables. So imagine that those are the places where you can put in your NOR gates, your NAND gates at a really low level. You can program your hardware, right? But over the years, we've added lots of more hardened blocks. For example, memory. Everyone needs to use memory. It's very, very expensive if you use those lookup tables and the NAND and NOR gates to create the memory. So instead, what you do is that we have multiple types of memory in there. We have something called block RAMs that have multiple read and write ports to it, so you can get really fast access to it. We have something called Ultra RAM that's a little bit bigger SRAM in there, and so on and so forth, right? We also have hardened DSP blocks. They are different than the DSP engines we're now introducing. So these are fixed point multiply accumulates that are put all over the FPGA so that you have memory, you have lookup tables around it, so you can create this really interesting data paths, whether it's video, networking, or what have you. So the use cases for this, some people, they use the FPGAs just as glue logic. You have a funky bus coming in, and you need to convert some things into something that your CPU can read, for example. So a lot of people are using it just for glue logic, and maybe that's some of our smaller parts. Some people are using these to really do massively parallel compute. Like you have an antenna signal coming in at the base station, and you need to do a lot of parallel processing on that before you can then eventually translate to a TCP/IP packet. Right? Some people are using really big FPGAs for emulation. So you're designing a new ASIC, and FPGAs are really good at a decent clock rate. You can actually simulate your design. And these are these really big chips, and maybe you have a bunch of those on a board, and then you have multiple of those boards, and you can simulate a big, big system with it at several hundred megahertz clock speed. So how do you program this stuff? Well, the easiest way for a software guy is that if someone else already wrote the accelerator that you're going to use, and you just use a library. But if you're not that lucky, then either you can go in and program in RTL code, so there's these hardware design languages like VHDL and Verilog, or something that we've been bringing out the last few years that at higher levels you program in C, C++, OpenCL, and then we translate that to state machines that's basically running in the FPGA. This is especially powerful for things like when you do matrix multiplication, right? If you have a loop, and then you can unroll that loop, so you do 100 computation at the same time. So every clock cycle, you do 100 iterations of the loop, for example, right? So if you write your code in the right way, you can get really parallel execution from it. So that's the FPGA. It's really fantastic in the sense that it can do a lot of really specialized things, and you can change that on the fly. Some people are putting FPGAs in the devices just as an insurance policy. They know that they probably didn't get their design 100% correct, so they want to be able to update that in the field later on. So that's sort of the global logic combined with some of the accelerator capabilities there. All right. So why do we see these heterogeneous systems coming up, right? I think there's two main reasons, and this I'm not going to, everyone knows this, that the old idea of using a CPU and then every year it will be faster and it will use lower power and so on and so forth, those days are long gone, right? We all know that. So instead, we started to do multi-core, but then we realized that it's hard to manage. You can't just scale and have more and more cores of the same type. So now really the solution is becoming using specialized accelerators, specialized engines for the task at hand. So that's really efficient from a hardware point of view, but it kind of screws up things from a software point of view because all these are programmed a little bit different. You have to manage them, and there are a lot of those kind of software issues. But we really have to go there because the workloads are continuing to go up, especially now when you have things like machine learning, which is really compute intensive. So that's one of the reasons. Another reason is really more about integration. So the devices out there, this is an industrial device. Maybe it used to be separate, different boards. Maybe you have one PLC board doing sort of running your app, if you will, connecting to the server, or nowadays to the cloud. You have maybe a control card, in this case, controlling a motor. So that needs to be real time. If something happens with the motor, you need to get those signals back and react really, really quickly. So you can't have your processor suddenly run and do something else. You need to be on top of things. So that's the short latency and deterministic behavior that you need from those kind of systems. You might have another board that handles safety issues. A lot of safety issues are coming in lots of different industries. It's been in industrial, automotive, of course, it's coming with the 262 standard. And safety is all about how do you protect the world from the device. You know, you don't want to have code that suddenly doesn't work anymore, so your brakes is not working, for example. And that's very expensive code. It takes a lot of money to safety certify a system. So you don't necessarily want to have all your code safety certified because it gets way too expensive. All right, so now we have these three boards. You want to save money, you want to save power, so you put it all in one SoC. But you still need to have this separation between general purpose, real time, and safety. Create some issues. So if we look at one of the current devices that we're going to use this as an example going forward here. So this is the Zynq MPSoC. It has 4 A53s, so that's the APUs, application processing unit. We have 2 Cortex R5s. Again, typically people use that for safety or real time and so on. We have a platform manager. That's a hardened microblaze. That's a CPU coming from Xilinx. We have the programmable logic, the FPGA fabric. So there you can put in what we call soft cores. So we have this microblaze. Now also from ARM, we have Cortex M1 and M3 cores. So those are soft cores. So you can put in many tens or hundreds, depending on the size of the device, of those in there as well. So you have all these different environments. Then you get, first of all the environments for each and every one of these cores. But then also some of the cores, they have different execution levels. So take the A53s, for example. They have EL0, where you run your user application typically. You have the EL1, where you have Linux and the kernels. You have the hypervisor, if you have one. That's at EL2. And EL3, there you have the firmware. And on top of that, you also have the trusted environment, trust zone, right? So you might have a trusted execution environment there, opt or something like that. So you have all these different environments where you're going to write your code. You don't necessarily know where the code will end up. So how do you write code that you can then put in all these different places? So that gets kind of tricky, especially since the operating environment is different. Linux, these days, I would say 80% of our customers, or more than that, are using Linux, typically on the A cores. But then they have companion operating systems, or bare metal, and those are open source, like FreeRTOS or Zephyr, but very often proprietary vendors. So there are lots of them out there, from Wind River and Green Hills, and so on and so forth. So again, in that ecosystem, we have to make it easier for people to be able to put these things together, to write code once, to configure these things. So how can we simplify this? Instead of the ad hoc, having a shared memory, and we all come up with our own way, it's kind of fun to write that code, right? An interprocessor interrupt, and you share a page or something like that. But why should everyone have to do that over and over again? So the things that you have to tackle then are, how do you configure these systems? How much of the physical memory goes to this core and this environment versus this? Which device hangs to Linux versus to FreeRTOS, for example, right? How do you lifecycle manage this? How do you, if you want to start up something, a new application on another core, and maybe it crashes, you want to be able to detect that, you want to be able to restart that. To do that, you actually have to know what devices belongs there. You have to idle those buses. You have to maybe reset the devices. There are a lot of things that needs to happen. Why should that be ad hoc for every device from Xilinx, or if it's from other silicon vendors as well, right? How do you share resources? Do you have a graphical card or a GPU? And maybe Linux is dealing with that, but you do want to do some graphics from VxWorks. How do you do that? How, for all these different operating systems, how can we make it easier for them to port in all these different environments from all these different vendors? So we have created something we call OpenAMP to try to solve some of these problems. So the OpenAMP Initiative, something we started about 4 years ago, and we're really trying to drive standards through open source. We find that that's the fastest way to get synergy, is to have example code out there, right? So it's really all about AMP, so that's asymmetric multiprocessing. We are both looking at the standardization, and using that term very in a liberal way here, because we're not writing big standard specs. We're more documenting the protocols that we're using, like vert.io, what different flags means what, and so on, so that we know that we're backwards and forwards compatible when we add new features, right? So OpenAMP, and then we have a clean room implementation of things that's already existing in open source, things like vert.io, remote proc, RP message. So those are existing in the Linux kernel. You can't just take that code. First of all, it's entangled with the rest of Linux a little bit, but also you can take that GPL code and put into a VxWorks or a Micrum RTOS. So we have written this clean room implementation of those, and that also means that instead of always having Linux as the master, we now can have a small RTOS as the master starting up Linux. Or you can have 2 MCUs running RTOSes and not have Linux at all. So OpenAMP currently doing these things, the lifecycle messaging and these things. We have a low-level abstraction layer that abstracts like memory and interprocess interrupts and things like that to make it easier to port your operating systems on the different environments. In the group right now, a bunch of companies, ourselves, Xilinx, we have TI, we have SD Micro, we have Mentor Embedded, Qualcomm, Wind River, Micrum, and so on. There's a bunch of people. Some people are actively contributing code. As usual with open source projects, there are a lot more people that are using it. And there's a bunch of companies using it that are not active in the discussions as well. So this is something that we are working actively. Something we're just starting to talk about is trying to attack the configuration issue. How do you configure, as I mentioned, what memory goes where? So that's a new concept that we call system device trees. that we just started, so this is just more informational. The question here is that you have a bunch of hardware that describes the SoC and the board. And then you have these different domains. You have maybe a Linux domain, maybe you have a trusted environment, maybe you have an RTOS. Or somehow we need to communicate the memory hierarchies, the buses, which physical memory goes here and there, which devices goes where, right? At Xilinx, our hardware engineers, they really like everything to be really, really programmable. So you can reprogram a lot of different things, like a device, where will it hang on? Will it hang to the R5s or to something else? But we need to specify those things. In our programmable logic, we can add new NICs, network interfaces, or a lot of new things there. We have to express those things. So we choose to express it with device trees, but we need to expand device trees from just looking at one address space to multiple address spaces. And the mental model of this is that you have a description of the whole system. You have then some input files that's saying that, well, for Linux, I need this address space, these CPUs. I need this much memory. I need these devices. Or I prune the system device tree and create a regular standard device tree as they exist today for the Linux environment. Do the same for the bare metal environment, for the free RTOS environment. And then we're working with our partners, and internally we are going over so that we're using device trees for our bare metal, for our free RTOS, and so on. So we're trying to make this a little bit of an industry standard. We'll see, it's very early on, so we'll see how we can do that. If we're successful, you can also use this to verify later on. When you integrate all these different parts, you can verify that the different partitions are not using the same memory space, for example, unless they're supposed to do. Because when you have these systems, it's really easy to screw up and just get one address a little bit wrong, and then both systems are going to hammer on the same device, for example, right? So let's talk about hypervisors. So we'll be talking about these AMP systems where we have different processor types. But really, a lot of our customers, what they want to do is you have 4 A53s there. I want to have an RTOS on that core, and I want to have Linux on these 2 cores. And I want to safety certify maybe things on another core. Well, it's not that easy, right? The A53s are really built more for an SMP system. Of course, you can have a hypervisor on top of it. So the use case is very, very similar. You typically pin the operating system to a particular core, so that's fine. You can use OpenAMP and the things, so we have ported OpenAMP to Zen. So you can use that for messaging, things like that. In the future, as we develop the system device trees, that's perfect to use for hypervisors as well, to allocate devices to the different partitions, the different domains in that sense speak. But there's one issue here, which on the A53 and A72s and those kind of Cortex-A class processors, is that the level 2 cache is shared. So that means that if you have something that's very time critical, you have a real-time partition that really needs to have a deterministic response time for something, well, then you have Linux running over here, and maybe Linux is doing some mem copy to big blocks. Well, that will then impact your real-time partition because the level 2 cache. Unless you can run from internal memory, and very often you can do that. We have several types of on-chip memories and things like that. Or if you run within the level 1 cache, then you're fine. But if you have a little bit of a bigger application, then you have a problem. It's not deterministic anymore. So we've been working together with some partners on a solution called cache coloring. So not going into the details of cache coloring, but at the very high level, what you're doing is that since the physical memory, each address is mapped to a particular cache line. So you can imagine looking at your memory in these blocks. Let's put colors of them that's repeating all over. But let's say that we allocate to the RTOS partition physical memory that corresponds to one of these colors, let's say green. And then we make sure that when we allocate the physical memory to Linux, we avoid the green parts. Then we know that Linux is not going to hit those cache lines. So that's what cache coloring at the very high level. You can look it up, and it's kind of interesting. So we have been implementing that in a hypervisor. The first one we implemented this is in the Jailhouse hypervisor. Been working with the University of Modena to do this. And the result is really, really encouraging. So you can pretty much do whatever you want on these other cores, running Linux and so on. And the real-time response time is very deterministic on the core where you need that using cache coloring. A little bit overkludged, and hopefully in future ARM cores, you have better ways of doing that with MPAM and things like that. But we live in a really pragmatic world, so you have to fix these kind of issues, right? Okay. So we've been talking about these heterogeneous systems with a lot of compute power. You might ask, well, those guys are probably very expensive. You know, can I use them in my system? Well, so Avnet is actually now introducing the Ultra96 version 2. So this Ultra96 board came about a year ago, I think. And this is the second version of it, second release. It's a $249 board. And it has the same processor that we've been talking about. It's really good for things like artificial intelligence, embedded video, those kind of things. Right? And it also is designed to be of the 96 board's form factor. And that means that the 96 board code will run on it as well. So you got that ecosystem going for you as well. So that's going to be released in May. And with that, you get the board, you get an SD card, but you also get the license to our, what we call the SoC tools, where you can write your code in C, C++, and it will translate that, not only translate the code and put that into the FPGA, but the rest of the code will do all the glue in between. So you just call a C function, and then we'll take care about the DMA transfers and all that stuff back and forth. So that will be available in May. The Ultra96 first version is available today, of course. All right, so we've been talking about SoCs, heterogeneous systems within one chip. What about if you have multi-chip solutions? So what's the situation there? And see if the clicker works. There we go. So typically what you do then is that you have some kind of CPU cluster. You talk over a bus like PCIe over to an accelerator, right? And that's a well-known way of doing things, been working for quite some time. The programming paradigm there is really that you write the driver, you set up some DMAs, you copy your data back and forth, you have the accelerator working on it, and get the data back, and so on. So the question is, can we make this a little bit more similar to this heterogeneous SoC course that we've been looking at before, right? And why would you do that? Well, it's really because the accelerators are becoming much more smart. You want to program in a different way. You want to have a shared memory for many use cases where the CPUs, they populate the data there, and then you can have an accelerator in parallel, maybe doing search on that data or manipulating smart memory, whatever you have. So suddenly you get this need for a NUMA kind of like of memory. So maybe the access times are a little bit different, but it should really look like one cache coherent memory block for the software on both sides. Then the programming model becomes much, much easier. So this is really what CCIX is all about. So it's really virtualized cache coherent accelerators. It's based on top of the PCIe standard, so things like discovery and all those things are compatible with that. But you don't need to have the drivers. You program it more like you do with a more coupled system where you have shared memory in between it, which for a lot of use cases really, really helps out. All right. So the CCIX Consortium, I think this slide is a little bit dated. It was 50 members. I think it's more than 50 members now, but it's really a big consortium. And the first devices coming out this year on the hardware side. Lots of people that then are supporting software stacks on top of it. So this is really a new, exciting way of doing accelerators that are connected to something else. And the nice thing is that with the CCIX standard, you can also use, so you have multiple dies that are connected really closely together and create those kind of systems as well. All right, that was my last slide. Do we have time for a couple of questions? Or?
I think that we do. Anyone? I think that was really fascinating and a great explanation. for OpenAMP and also CCIX. Anyone have a question? There was a lot there. No one?
Or everyone is... When's coffee, exactly.
All right, so Tomas, thank you so much for joining us and sharing that with us today. We really appreciate it. That was great.